Okay, so today's plan, pretty simple, just continuing on with chapter 4, probability, going through part 3 of the PowerPoints on section 4.4 on counting. So that's the goal for today. The thought for today, the quote of the day, kind of not really a quote, but thought is from Scottish philosopher David Hume from the 1700s. Um, this idea that's sometimes called Hume's guillotine. And it's a guillotine in the sense that it kind of slices in half two modes of thought. And the argument is that we can't derive ought statements. So like what ought I do or what, should I do from is statements from statements of fact about the world. So we can't derive moral statements from statements of fact. The goal of science is really to establish statements of fact. And that's kind of part of, you know, that's where statistics kind of comes into play is can we uh, can we make more accurate statements of fact about the world, what is true about the world? And we ought to be careful not to encroach on the ought side of things from our scientific perspective. It might feel like we should be able to somehow say because the world is this way, we ought to do this other thing. But really, once we start saying what we ought to do, we're implicitly, at the very least, assuming a bunch of value systems and all of that kind of thing. So we want to be careful to really kind of, stay in our lane, so to speak, when we're dealing with either um, scientific type knowledge that says what is true about the world or statistical uh, knowledge that is attempting to say what is true about the world. Okay, so the plan today is to discuss counting. And we've seen that if we want to compute, say, probabilities of events, we need to count the number of outcomes in the event and divide by the number of outcomes in the sample space, provided the outcomes are equally likely. And we've seen that most of our setups so far have been pretty easy to count the number of outcomes in an event, like maybe rolling an even number on a fair six-sided die. Well, that's just 2, 4, or 6. That's 3 different possibilities. Or counting the number of outcomes in the sample space also has tended to be pretty straightforward, although we had a couple of scenarios like, say, rolling 2 dice, we have 6 times 6 or 6 squared different outcomes, or 3 dice, 6 cubed outcomes. So we might have had to think a little bit more about that. But so far, our counting demands have been pretty minimal. But we did kind of maybe get a clue into the fact that there could be some events and some sample spaces that are where it's a lot harder to count the number of outcomes. And that's really what we're going to focus on today. Okay, so how do we count outcomes either, say, in events or in sample spaces, whatever it may be, that aren't just as straightforward as us just being able to enumerate them or count them very easily? So we start off with this fundamental counting rule. And it says, suppose that a probability experiment consists of n ordered trials. So I know which one is first, which one is second, and so on, each of which has k sub I possible distinct outcomes. Then the total number of unique sequences of outcomes is the product of those. So I like to think of this as, say, n boxes, and I want to fill each box in with an outcome. So in a simple case, maybe I'm flipping a coin n times, and I just want to put either H or T into each of these boxes, right? So I might have 2 choices for the first box and 2 choices for the second box, 2 choices for the first flip, 2 for the second flip, and so on. But in a more complicated case, I might have a certain number of choices that could go into the first box. Maybe that's I roll a 6-sided die or something, so that could be 6, and then another number of choices that could go into the second box. Maybe that's flipping a coin, heads or tails, so I have 2 choices for that one, and maybe the third one is drawing a card from a deck of cards, and there's 52 choices. I might have say, K1 choices for the first box, K2 for the second box, and so on to Kn for the nth box. And how many unique sequences of outcomes are there? Or if we wanted to call the sequence itself the outcome, then how many outcomes are there? The number of outcomes is K1 times K2 times through Kn. And kind of the idea is, let's say we flip a coin and roll a die, like if we can pick heads or tails for the first flip, and then we can do 1 through 6. I don't know why my line is a little wonky there, but went a little off kilter. So kind of for each of my choices, heads or tails, I could flip a heads, then also get 1, 2, 3, 4, 5, or 6. Or I could flip a tails and also get 1, 2, 3, 4, 5, or 6 on the next one. So there are 2 options for the first one, each of which leads to a potential 6 different options for the second, and so on from there. Okay, so let's look at some examples. Let's start with a fairly straightforward example. How many possible outcomes are there on 4 flips of a coin? How many possible sequences of heads and tails? Now be a little bit careful here. What exactly are we saying? How many different sequences of heads and tails are there? That's not to say, 0 heads, 1 head, 2 heads, 3 heads, 4 heads. We don't want to say there's 5 different possibilities of, say, number of heads on 4 flips. That would be a different question. What's the number of unique sequences? So like heads, tails would be a different sequence than tails, heads, or heads, tails, heads. So each of our 4 trials, each of our 4 boxes, so to speak, we want to fill in each of these boxes with a head or a tail. There are 2 choices for each of them. And my total number of outcomes then should be 2 times 2 times 2 times 2, 2 to the 4th power, or 16 outcomes. This is actually a small enough sample space we can just enumerate all of the outcomes. So let's look at what that looks like. If I just want to write out the sample space, I have 1 outcome where I get all heads. I have 4 outcomes where I get 1 tail. The 1 tail can be in the last place, the second to last, the third to last, or the first. Coming from the bottom, I have 4 outcomes where I get, or sorry, I have 1 outcome where I get all 4 tails, and I have 4 outcomes where I get exactly 1 head, and that head can be in the last place, second to last, second place, or first place. And then I have some outcomes where I get 2 heads and 2 tails. These are actually the hardest ones to enumerate. But I have a heads, tails. I can move that first of the 2 tails forward 1. You can think of it that way. So heads, tails. I can move that first tail forward 1 again. Tails, heads, tails. Then I can move the second tails forward 1 and the first tail up to abut it. Heads, tails, heads. Keep that second tail in the 3rd place. Move the first tail forward 1. Tails, heads. And then we can move our second tail forward 1 again, and that leaves us with tails, heads, and that's it. So we can kind of work our way through like that. And those are our 16 outcomes. Now, with just 4 flips of a coin, it wasn't, too terrible to enumerate those all, but we could see it was actually quite a bit of work to make sure that we got all of them and didn't repeat any. We had to be very systematic about how we did it. And you can imagine if I was dealing with 4 rolls of a 6-sided die, or if I was dealing with, even maybe 5 or 6 coin flips would be insurmountable, but certainly 8 or 10 coin flips. This could get very difficult very quickly, at the very least, very time consuming. And this is where things like these more abstract rules are super helpful, right? rather than enumerating all the outcomes and actually counting them one by one, being able to rely on a fundamental rule like this fundamental counting rule means that if I have 10 coin flips, the answer is 2 to the 10th. I don't need to write out 2 to the 10th or somewhere around 1,000 different strings of 10 heads and tails. Okay, so how many standard Pennsylvania license plates are there? So I'm sure we've all seen the standard PA plate that has letter, 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 and then the keystone symbol, and then number, 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 number. Right, 3 letters and 4 numbers. Note that the 3 letters have to go first and the 4 numbers have to go last. We can't you know, we can't just mix the characters around any way we like. So really I have 7 boxes I need to fill in. The first 3 boxes are going to be letters. So there are 26 choices for each of those. And then our numbers, be a little bit careful with the numbers. You might think 9 at first, but remember 0 is a perfectly valid number to put in here. So 0 through 9, there are 10 numbers for each of these boxes. Another thing that we haven't really pointed out, but we've been kind of doing implicitly is we're doing this with replacement, right? That was kind of obvious in the heads and tails example, but a little bit less obvious here. So let's point that out. We're doing this with replacement. In other words, AAA 4444 is a perfectly valid license plate. So if I use A for the first letter, I can use it again for the second or third letter. I'm kind of, I have a bag of letters over here. I'm pulling out one out. I get an A. I record it for the first letter. I put that one back. I can pull it again on the second or the third letter. Or same for the numbers. I could use, 1919 or something like that. And that's a perfectly valid license plate. It's not like I've used a number for, say, the first of the 4 numbers. If I use a 1, it's not like I can't use a 1 again. So we're implicitly doing this with replacement. But we do see that we get 26 cubed times 10 to the 4th as the number of unique PA license plates. This, of course, doesn't, count the ones that they might filter out if they, if they spell something that they don't want really floating around on a license plate. But we see somewhere in the ballpark of 176 million different license plates. I think there's something like 10 million people in PA, so 17 license plates per person, probably plenty enough. And that, of course, doesn't say anything about all of the, one-off types of license plates, the, river conservation ones or water resource conservation or the railroad ones or all of those kind of fun ones, these would just be the standard ones. Something interesting to think about is all of these password rules that we seem to be constantly battling with today, right? So we can ask a question like, how many possible passwords are there consisting of 8 lowercase letters? So again, we have 8 spaces to fill in or 8 characters to choose. So a password is just a sequence of characters. It has to be in order. If my password is AAA, BBBB, then BBBB, AAA doesn't count. So it has to be in order. But again, I can reuse characters from one space to the next. So order matters. It's not just that you get the right 8 characters, they have to be in the correct order as well. And we're choosing with replacement. Okay, so how many unique passwords are there? Well, if I have lowercase letters is all that the characters I get to choose from, I have 26 choices for each box, or the number of passwords. is 26 to the 8th power. And if we do that on the calculator, that turns out to be around 2 times 10 to the 11th. Let's actually do that really quick here. So I need 26 to the 8th power, so I type in 26. And then for power, I just use my caret symbol here above the divided by sign, just above the string of blue buttons. For the operations, I have a caret, 26 to the power 8, hit enter. And we have to be a little bit careful when we're reading these numbers off the calculator. You might look at this and think, oh, it's like 2.08. That doesn't sound right. Why would I only have 2 or something passwords? Well, this E11 over here, so 2.08 E11, E means kind of like exponent, something like that. It means times 10 to the power 11. So be careful when you're interpreting the result coming out of your calculator. We know this should be a really big number. There's going to be a lot of passwords that, uh, a lot of these strings of 8 digits, or sorry, 8 letters. We know there's going to be a lot of them. It should be a big number. It's certainly not going to be a number like 2, and it's certainly not going to be a decimal number like this uh, for the number of passwords. But 2 times 10 to the 11th, about um, quite a few passwords, right? 10 cubed is 1,000, 10 to the 6 is a million, 10 to the 9th is a billion. So 10 to the 11th is like 10 to the 9th times 100. So this is like 200 billion passwords. So 200 billion passwords, somewhere in that ballpark. Why do we care about the number of possible passwords? Well, because if somebody's trying to hack into your account and they know that it's an 8-character password, and if they knew that it was 8 lowercase letters, if that was, the rules for this password system, well, then if they were just brute forcing their way in, there are 200 billion possibilities. I mean, you could think of a really dumb password like, your password is either the number 0 or the number 1. It's pretty easy to brute force that, right? I try 0. If that doesn't work, then I try 1 and it will work. So with 200 billion passwords, I mean, that's impossible passwords. That sounds like a lot. But, kind of on the downside, computers can do things really fast. So somebody can program a computer to just keep trying like all A's and then all A's, then a B, and then all A's, then a C, something like that. And it could probably make it through that 200 billion passwords, maybe faster than you might think. And that's to say nothing of the fact that almost nobody is going to choose, Q, V, X, whatever, C, B, A, D, or however many letters that was. Right. Like probably 10% of people are going to choose the word password. So there's a couple of problems here. One is that 200 billion sounds like a lot, but computers do things really fast, and it turns out that it's not all that much. And the other problem is that, well, with just letters, people tend to pick words for their passwords. And then you can write a computer program that just says, hey, try a bunch of 8-digit words or 8-letter words. And that's going to make the number of passwords that people are likely to choose much, much smaller. Now, as an aside, on the kind of the plus side for security, there is actually a pretty darn easy way to thwart these brute force attempts, even things like dictionary attacks, even, plugging in words that people are likely to use. You just say, if you enter the wrong password 3 times, you have to wait 5 minutes before you enter a password again. Like, that's usually not that big of an issue for people to just have to wait a few minutes. And but for a computer that's trying to enter, a million of them a second or something like that to get through these 200 billion passwords really quickly, that's a big deal, right? If you can only try a few of them every 5 minutes, it's going to take you a really, really long time to get through any appreciable amount of possible passwords. So in my mind, that's probably the number one thing that they can do um, to stop people from kind of brute forcing your password like this. But let's say we want a system that's a little more secure. We're still going to use 8 characters. So we still have 8 spaces. So this had 8 spaces, this has 8 spaces. So still an 8-character password, but now it can be lowercase or uppercase letters, which we can distinguish between, numbers, or say any of 10 special characters. So now I actually have 26 lowercase letters, 26 uppercase letters. I have 10 numbers, 0 through 9, and 10 special characters, exclamation point, star, things like that. Or that's, well, 52 plus 20 is 72 choices for each space. I have 72 choices for each of my 8 letters or 8 characters. I keep mixing up characters, letters, and digits for some reason, but I'm kind of using them roughly interchangeably here. So I have 72 choices for each of my 8 characters, or the number of these 8-character passwords with the expanded character set is 72 to the 8th, or about 7 times 10 to the 14th. So for all of this hassle, how many times have you gone to make a password and it's like, oh, you didn't use a capital letter. It's like, okay, so use a capital letter. Then it tells you, oh, you didn't use a special character. Like, it's like, will you just tell me all of the requirements to start with? There's actually a funny game. I've never played it. It sounds like it's extremely frustrating, but it's one of these like text-based online games where you like try to come up with a password and you have to like obey all of the rules of the system. So you like type in something as your password and it says, no, that's not a valid password because you didn't meet this rule. But it doesn't really, I think it doesn't tell you what the rules are at the beginning, or like each time you don't satisfy the rules, it adds another rule or something like that. I don't know. I've seen like uh shorts or reels or whatever where people, play this game or something. So I don't know. It
It's
just
it's
sounds familiar.
literally called the password game.
Oh, it's called the password game. Yeah.
Yeah.
Yeah, so if you want to make yourself frustrated, or if you want to practice being able to create passwords for these systems, then you can play the password game. Uh, it seems like it's more like a joke than an actual game, I think, but I'm not 100% sure how it works. But that's what these always remind me of. They always make me think of that. Or there's that great meme that's like, enters password wrong, enters password wrong, enters password wrong, reset password. You can't use any of your last, whatever password. You can't reuse your password or something like. So the password they typed in to reuse was or to change it to was their password. Um, but anyway, so all of these extra characters and things, you know, doubling the number of letters and adding in numbers and special characters got us about 1,000 times as many passwords. Not a huge benefit. I guess maybe it got us about 4,000 times as many, going from 2 times 10 to the 11th to 7 times 10 to the 14th, but on the ballpark of 3 orders of magnitude. So what happens if we just were to stick with lowercase letters, but we were to use a 10-character password instead of an 8-character password? So there's 5, 6, 8, 9, 10. So if we made it a 10-character password, adding 2 more characters, but only lowercase letters, no uppercase, no special characters, no numbers, 26 choices for each. Now the number of passwords is 26 to the 10th, or about 1 times 10 to the 14th. So by just making our password 2 characters longer, we actually got about the same order of magnitude increase as by expanding our character set by more than twice as many, by almost 3 times as many. Right, what's the difference here? If we increase the length of our password, we're increasing the exponent. Whereas if we increase our character set, we're increasing the base. And we should know that exponential growth is much faster than polynomial growth. If I increase an exponent, that's going to make my number much bigger, much faster than if I increase the base. And that's something you're tending to see these days is going to passphrases, and they don't really care very much if they're all letters, at least, the smart ones don't really care. Going to things like passphrases where it's like they actually want a 14 character or 16 character password. And what people will typically do is, the recommendation is to pick some words, but make them words that people aren't likely to like use. Don't pick a word like computer or Apple or something like that. But pick kind of offbeat words, or say four words that don't go together too often. And if you really want to make your password strong, misspell one or two of the words slightly. And that's much better for humans to be able to remember. And it's because the length of the password gets really long, it's impossible to brute force it. And even something like a dictionary attack is still quite difficult. So that's where I think things are going these days. That combined with the systems that lock out after a couple of attempts for just a couple minutes, it's a mild inconvenience to the user, but it essentially thwarts, the ability for computers to just input tons and tons of passwords. And then, of course, things like two-factor authentication. There are a lot of things that are working in conjunction here. But historically, this was always the way that the things tended to go, was just increase the character set. But the problem is when you make security less user-friendly, when you make it harder for the actual users to use, then the actual users find cheat ways around it, basically, right? Like they'll end up reusing the same password over and over for a really long time with maybe a little minor modification or something like that. But they'll figure out, how can I actually use this system that's not meant for me to be used? That's just kind of put together in a reactionary way, not really in a thoughtful way. And saying things like you have to use, at least 3 of these 4 things. Well, most people are going to capitalize the first letter and put 2 numbers at the end that are probably likely to be their birth year or their birth date or something like that. So, like, have you really done very much there to thwart, computer attacks? Not really. But I think that our current way that we're going with combination of passphrases and lockouts makes a lot more sense, because we're increasing the exponent rather than increasing the base. Increasing the base makes it harder for people to use and not that much harder for computers to break into. And increasing the exponent makes it not much harder for people to use and much harder for computers to break into. Okay, this is kind of a little bit of an aside, but I think that it's kind of a really cool one. So interesting question. If we have some genetic material that's, say, roughly the size of the human genome, how many different genetic sequences are there? So the human genome has about 3 billion base pairs. So you can imagine it as a DNA ladder like this, where you have 3 billion base pairs. And it's important to note that, roughly speaking, A always matches with T and C always with G, unless something has gone quite wrong. So, if you know the letter on one of the sides, then you effectively know the letter on the other side as well. So we really have, like, there might be, say, the coding strand here. That's really all that we care about, is one side of this. The other side is not independent. The other side is essentially just a copy of the first side. And if we just imagine sticking all the chromosomes together, end to end, then we have about 3 billion of these spaces, so to speak, to fill in. So I have box 1 could be A, T, C, or G. Box 2 could be A, T, C, or G, and so on. and I have 3 billion boxes. There's not a lot of choices per box, but there's a whole lot of boxes. So what's the number of human genomes, number of possible, maybe we shouldn't call them human genomes because, not very many of these would look like a human, but uh, but what's the number of possible genomes the same length as the human genome? Well, there are 4 choices per box. To the power, how many boxes are there? To the power 3 billion. 4 to the 3 billion power is something like, what do I have here? 10 to the 1 billion or so. 4 cubed is 8, so let's call that about 10. So it's about 10 to the 1 billion. Or it's like a 1 with a billion zeros after it. Like if you think of the biggest book that you have, it probably doesn't, and certainly doesn't contain a billion characters. If you pull down your copy of War and Peace and you replace all of the letters in there, put a 1 at the beginning, replace all the other letters with zeros, and flip through the book, and it's just all these zeros. That's not going to be a billion zeros. So this is an enormously large number. It's about 1 to 2 gigabytes of data, which, by the way, kind of brings some appreciation to the amount of data storage that we have in random things like phones or little teeny tiny SD cards or something these days. That's about 1 to 2 gigabytes of data. And it's stored in, roughly speaking, each and every cell. Maybe not red blood cells, and some of those, the biology folks can come up with counterexamples, but roughly speaking, every cell. So when you wipe your hand over your arm and a bunch of random cells kind of slough off and fall to the ground, like you've probably just, threw to the ground as much data as your entire hard drive can store, or something like that. So it's really crazy how much, data is stored in each and every one of our cells, a couple of gigabytes worth of data. So these numbers can get very large very quickly. It's also, kind of crazy to think that anything works with copying genetics whenever cells need to divide, and the DNA needs to copy itself so that we have 1 copy in each cell after the cells divide. How do 3 billion bases copy reasonably efficiently and reasonably effectively, and without too many errors and those kind of things. It's fascinating machinery in our cells. Okay, so we talked about the fundamental counting rule, where we multiply the number of choices for each box or for each space together, and that gives us the total number of outcomes, the total number of sequences. So let's try to expand out from here. So there's a classic problem in computing, and also it also touches on other fields, but mainly in like computer science. It's called the traveling salesman problem. And this is the idea. Think back 50 or 70 years ago when people actually went door to door to sell things sometimes. Suppose that a salesman needs to travel to 10 different US cities to meet with clients. The salesman would like to choose the quote best itinerary for his needs. That might look like choosing the lowest cost or the lowest total distance, lowest travel time, something like that. And we want to come up with, this itinerary, figure out how much it costs, whatever we're defining as cost. Another itinerary, figure out how much it costs, go through all of them, and then pick the least costly one. There's only 10 different cities. That doesn't sound like a bad problem to do. So how many of these costs we have to compare? How many different itineraries could there be? So let's say we have our salesman. We have, let's say, a poorly drawn version of the US here. And our salesman has 10 different cities to visit. Now we can kind of tell just heuristically, just by looking, let's say that, maybe it'll choose to start here. We can tell that, maybe something like this would be an efficient, somewhat efficient path. And that something like this probably wouldn't be for essentially any of these metrics. But computers aren't so good at this, so computers are going to want to brute force through all of these itineraries. So we're thinking our salesman has this bag of 10 cities, maybe Pittsburgh and LA and Orlando and Wheeling and Cleveland and whatever. He's got this bag of 10 cities and he's got 10 slots. Which city is going to be the first for him to visit, the second, the third, and so on through the 10 slots. So his itinerary is going to be this sequence where order matters. If you go in a different order, it's a different itinerary. Right. So the sequence is going to be order matters. But note that he's going to do this without replacement. He's not going to visit Pittsburgh 3 times. This is without replacement. So this is a little bit different than our previous setup, right? Because if he puts Pittsburgh first, well, Pittsburgh's not available to be chosen for the rest of the itinerary, right? He's not going to come back to Pittsburgh again. He wants to visit each of the 10 cities exactly once. So how many choices does he have for which city to put first on the itinerary? There are 10 cities in here, and there are 10 spaces on the itinerary. He's got 10 choices for which one to visit first. He could visit Pittsburgh first, or LA first, or Orlando first. Any of the 10 can go first. But once he pulls one out of the bag, once he says, okay, I'm going to visit Pittsburgh, that's not available to be chosen for any of the future spaces. He visited Pittsburgh already, not going to visit there again. So there's 9 left for what comes second. Once the first space has been filled in, that city is no longer available for any of the future spaces. For the second space, you fill in the first city, then there's 9 left to fill in the second. Once he fills in the second, maybe go to Cleveland next. That's not available for any of the future spaces. There are only 8 available from that point forward. Once he chooses the third city, what fills in the third slot? There are only 7 left for the next one, and so on down the line. Our fundamental counting rule still applies here. We still just have a bunch of spaces that have different amounts of choices for each of them. The without replacement detail is taken care of in the decrementing here, and the fact that each future space has 1 fewer city to choose from. So what are the number of itineraries? It's 10 times 9 times 8 times, and so on, times 3 times 2 times 1. And we have a name for this. We call it 10 factorial. And it actually, the symbol for factorial is the exclamation point symbol. Okay. And we can do this on a calculator, and we would get about 3.6 million different itineraries, probably a lot more than we would expect. Certainly, I wouldn't want to go through all these itineraries by hand. And I wouldn't even want to write them out by hand, let alone for each one try to compute what's the cost, either the cost for all the plane flights or the travel time or whatever it may be. So this traveling salesman problem is interesting because with even, say, 10 cities, it kind of gets out of control really quickly. And you can imagine somebody like FedEx or UPS that every single day, a single UPS driver responsible for maybe a single geographic region, I don't know, what do they have? 200, 300 packages that they have to come up with a route and deliver these packages in an efficient manner. How do you come up with what's the most effective or efficient route for this person to travel. And that's to say nothing of the problem of how do we decide to split up geographic areas between drivers, or, you know, uh, in the holiday season when things are busier. I mean, that one driver isn't going to be able to cover the same geographic area in November, December as he can in February or something when the load is a lot lighter, right? To say nothing of all of that complexity, even just a single driver on a single day with, I don't know, whatever it may be, 150, 200 packages to deliver. You can imagine, what does 150 or 200 factorial look like when 10 factorial is 3 million. So this is a very challenging problem. And actually, one of the coolest approaches I've seen is Carnegie Mellon has I don't know what, it's not really a department, it's an institute, I guess. I don't know, a collaboration between departments, the Human Computer Interaction Institute. And actually what they did is they were doing, this was quite a while ago now, probably 15 years ago now, so I'm sure there are better approaches these days, but they were they had like a glass table where humans would stand around, and the computer would start going through, pick an itinerary and evaluate the cost, pick another itinerary, evaluate the cost, and then pick the best of those two itineraries. And then it would pick a third itinerary, evaluate the cost, pick the lowest cost between the previous best and the new one. And it would draw out its best itinerary so far. So it might do something like this, just by chance have worked its way into that, and then something like that. And the humans would say, I mean, obviously with much more complicated scenarios than this one, but the humans would circle this area and say, don't investigate here anymore. Don't change any of those. Those look pretty efficient, right? It doesn't look like I can do these three much more efficiently than that, but it looks like there's a lot of inefficiency there. So maybe take a look at this area. So the humans would direct the computer and say, this area just looks bad, so focus your efforts here. And the computer would, kind of go through that area and try to make it a little bit better. So the computer might get to, oops, where did my blue pen go? The computer might get to, I don't know, something like this. And then the human would say, this looks good now, and this looks good. Focus your attention on this part. So by the human saying, just heuristically, like, what seems efficient to me, that's a very human thing to do. And the cranking through lots of different options is a very computer thing to do. So like, can we get the humans and the computers to kind of collaborate, each doing what they do best? I thought it was a cool approach to the problem, but it's a pretty famous problem in math and computer science, because it becomes so intractable so quickly. Even with just 10 stops, we're already over 3 million itineraries. Okay, it would be nice to have a notation for something like this. We can probably suspect this is going to come up every once in a while, so having a notation for it is nice. I already mentioned this 10 factorial is how we would write this. So what do we define as a factorial? Well, the factorial of a positive integer is the product of that integer with all other positive integers less than it. So just like up here, 10 factorial is the product of the number 10 with all other integers less than it, other positive integers less than it, 9, 8, 7, 6, 5, 4, 3, 2, 1. Note we can also define this recursively. It's a little more accurate to define it recursively. So we say n factorial is 1 when n equals 0. In other words, 0 factorial is defined to be 1. That might seem very strange, but there's a couple different ways that we can approach this. One is, well, we're making a definition. We're making a definition, so we get to say what this means. And this is how we choose to define it, simply because when we look at some future definitions, it's going to make those definitions not have to have a special case. That's one way to look at it. This just kind of meshes nicely with the way we want to define other things that are quite sensible. Another way to look at it is if I had 0 places I want to travel to, how many itineraries do I have? Basically just one, right? I just have to sit on my couch, go nowhere. If I had 1 place I want to travel to, then I have 1 itinerary, just go to that place. But if I have no places I want to travel to, well, I just don't go anywhere. So 0 factorial could be 1. From that, whatever that perspective as well. And another way to think of n factorial is again, or the other case, sorry, is defining it recursively, n times n minus 1 factorial. So defining n factorial in terms of n minus 1 factorial for n bigger than 0 and integer. So in other words, 10 factorial is 10 times 9 factorial, right? I can just split the 10 off the front, and what's left over is the product of 9 with all other positive integers less than it. Or 9 factorial is 9 times, if I split the 9 off of that, then I'm left with the product of 8 with all of the other positive integers less than it. Right, so we could define factorial recursively like this. This is actually a pretty common intro to programming type exercise. If you're writing your first recursive program, it might be something like, say, Towers of Hanoi, but that's kind of complicated to manage the sizes of all the things and all that. But a really simple one is just write a factorial program. You need a base case like this one here, because if I just keep saying, well, decrement by 1 factorial each time, eventually I get down to 1 factorial, and then that leads to 0 factorial, which we've defined to be the number 1. So that's our base case. We just kind of keep putting more and more stuff on the stack, and then we hit our base case. 0 factorial is 1, and then we can just input that into all of the function calls that we have remaining on the stack one by one. So you might have seen this if any of you have done some basic programming, either Python or something like that. If you've ever done recursion, you might have seen this. Or another common one is the Fibonacci, I think, is another common one to do. Okay, so there's an example. Oh, and on the calculator, so how did I get this number? Well, I could have typed in 10 times 9 times 8. That would have taken a while. But the calculator has factorial in it. So I'm going to just kind of show you where it is first, and then we'll look at how to use it. If you see this button here that says math in all caps, there's the 2 colorful buttons, second and alpha, the yellow second, the green alpha, and then below that is math. So click or hit math, press math. And then you'll notice 2 things. We have a kind of left and right set of drop-down menus here. The one that's selected now is actually called math, but to the right of that is number, and then complex CPX, and then probability. We can change which menu we're in by using the left and right arrow keys. I can either use the right arrow key a couple of times to get over to probability, or nicely enough, it wraps around, so I could use the left arrow key to get over to probability as well. So again, from the home screen, if you ever get stuck in something, just second quit. We'll bring you back to this home screen. We go math, and then we see we're in the math kind of submenu here. We want to go right a couple or left to wrap around to where we see we're in the probability submenu. And we see things like the first choice here, rand, picking a random number. There's options 2 and 3 here, which we'll actually get to in a minute. But there's option 4 here, which if you, blur your eyes a little bit, looks like an exclamation point. Now, if I hit enter, it just puts an exclamation point after answer. That's kind of confusing. But if I want to do 10 factorial, I would enter the number, say 10, and then I would go to my factorial. I go math, go over to the probability submenu, and just go left to wrap around. And then I can either navigate down to 4, the factorial, and hit enter. Or if I wanted to be even quicker, I could just hit the number 4 and select the fourth option here. So whichever way you would like to do it. And that'll enter the factorial symbol after whatever you have typed in. So I want 10 factorial. That's where I got that 3.6 or so million. Okay, so what is the factorial rule then? We see that it has its basis in the fundamental counting rule, and really all of our rules are going to build off of that fundamental counting rule sitting at the base of all of this. But this is kind of a special case, but it's a special case that comes up often enough that we just kind of consider it its own rule. If we have n distinct items, n different cities, 10 different cities, to be allocated to n slots that we want to visit in order, so we have an itinerary of 10 different places to visit, where order matters because if I visit Pittsburgh first, then LA, that's different than if I visit LA first, then Pittsburgh. Where order matters, where a different ordering represents a different outcome or a different sequence, then the number of unique outcomes is n factorial. That's not just a really excited statement, that's number of outcomes is n factorial. Note that it would be kind of a silly question to ask if I wanted to allocate n distinct items to n slots and order didn't matter. There's kind of just only one way to do it, right? Just put all the items in all the slots. So, um, so if we're allocating n distinct items to n slots and order matters, then the number of unique outcomes is n factorial. What would be an example where maybe we're allocating some things, but order does not matter? Well, the classic example there is like a poker hand, right? If I get a royal flush, if I get ace, king, queen, jack, 10 of hearts, let's say, it doesn't matter if I picked up the ace first and the king last, or the king first and the ace last. I'm just holding 5 cards in my hand. It doesn't matter which one I picked up first or third or fifth. So that would be an example where order does not matter. Now, of course, if I picked up the whole deck and said order doesn't matter, that's kind of a boring problem because, you just have all of the things that if there were 10 things to allocate to 10 spaces in order to not matter, you just put all of the things in all the spaces, and there's only one way to do that. Okay, so again, the traveling salesman problem. The number of itineraries is n factorial, where n is the number of cities, or for 10 cities, it's 10 factorial. Okay, and then we have 2 variants of the traveling salesman problem that I've made up. I'm sure I'm not the first one to think of this, but we're no longer in the standard traveling salesman problem. So suppose we have a lazy traveling salesman. The salesman is supposed to travel to 10 different US cities to meet with clients, but only plans to travel to 6 of the cities and hope his boss doesn't find out. How many distinct itineraries will the salesman have to choose from now? So just like before, the salesman has, let's say, this bag with 10 different cities in it, whatever it was, Pittsburgh, LA, Orlando, Wheeling, Cleveland, and 5 more, so 10 cities. But now our salesman only has 5 spaces. Or sorry, 6 spaces. Going to travel to 6 of them. So he's got 6 slots to fill in. There's 6 that he's going to travel to, and there's 10 he could choose from. Now, these are still physical visits. These are still itineraries where order matters. So it's not just a question of which six he pulls out, but also what order those six are in. Right, Pittsburgh to LA to Orlando to Wheeling to Cleveland would be quite an inefficient path, but maybe Cleveland to Pittsburgh to Wheeling to Orlando to LA would be a lot better, right? The same cities, but in a different order would be a very different itinerary. Well, he's still got 10 choices for the first space, just like above, right? So he's still got 10 choices there. And he's still in the situation where if he chooses one city for the first space, he's not going to come back to that city again. So this is without replacement. Once we have allocated a city to one of the spaces, once we've taken something out of the bag and put it in a space, we're not going to use that one again. So that means there's 9 left for the second space. Once he uses one more city, there's 8, 7, 6, 5. The main difference here is that we've kind of stopped allocating at some point. As kind of a side note, a little more abstractly, we can envision this as picking out 6 of the cities to put in a specific order, and then leaving 4 cities in the bag. If I leave a city in the bag, it doesn't have an order. It doesn't matter if I chose to not pick LA first or chose to not pick LA last or something like that. The 4 that are left in the bag that I'm not visiting, there's no order to them. If I rearrange the ordering that they're listed in the bag, that doesn't do anything. I'm just not visiting any of those cities. It doesn't affect the itinerary. But if I reorder any of the ones that I am visiting, that does affect the itinerary. So you could think of it as just splitting these 10 cities into 6 in one group where order matters and the other 4 in a group where order does not matter. It's another way of thinking about it. But what's the number of itineraries now? The number of itineraries is, well, 10 times 9 times 8. But we don't go all the way down to 1. We stop at 5. 10, 9, 8, 7, 6, 5, and stop there. Now I look at this and I say, okay, I mean, that's not too terrible to type into a calculator, but if there were 100 cities he could go to, and if he wanted to visit 12 of them, I mean, 100 times 99 times 98, 12 of that's going to get to be cumbersome to type into a calculator. I would like to do a little more work here to maybe rephrase this in terms of our previous factorials. It almost looks like I have something that wants to be a factorial here, right? This like wants to be 10 factorial, but it's not quite. Well, what could I do? Maybe I could force the issue, right? If you think of like quadratic equations, sometimes we complete the square, and we complete the square to make the variable bit look like a perfect square, because that makes our lives easier. We'll do something similar here. We'll kind of like complete the factorial. I say it would be super nice if I had a times 4 times 3 times 2 times 1 at the end. I don't have that, but I'll stick it on the end. But of course, if I do this and just left it like this, I would change the value. So to maintain the same value, I'll also divide by it. So I multiplied by 4, 3, 2, 1. I divide by 4, 3, 2, 1 as well. So net, I've just multiplied by 1. I haven't changed the value. But I actually see that I have a ratio of 2 factorials now. I have 10 factorial divided by 4 factorial. I kind of have like my original number of itineraries if I was going to visit all the cities divided by the number of rearrangements stemming from the 4 that I left in the bag that don't have an order mattering. Right, so this over 4 factorial is kind of saying, well, these 4 that I left in the bag up above in the previous problem, their order would have mattered, but now their order doesn't matter. So I'm kind of, if I just said 10 factorial, I'll be overcounting by a factor related to how many orderings there are of the ones I left in the bag whose ordering no longer matters. So I correct for that by dividing by 4 factorial. I could think of it either way. I could think of it more brute force in terms of the fundamental counting rule, or I could think of it in relation to our factorial rule and the fact that this segment of our 4 leftover cities, order no longer matters. They're just left in the bag. We're just not visiting them, and order doesn't matter for those 4. So we can go to our calculator and we can do 10 factorial. Remember, if we go math, go to the left to bring up the probability submenu, and we can actually just hit 4 to put in the factorial sign. And then we divide by 4 factorial, 4, math, to the left, select factorial, either go to it and hit enter or hit 4. And we see we get 151,200. This is the number of itineraries, IT, number of itineraries. That doesn't look like an IT, but that's what that says, is about 151,000. A heck of a lot less than the 3.6 million we got up here. Still only 10 cities in the bag, but we're not visiting as many of them. And of course, we know that the fewer of those cities we visit, if we were only visiting 1 city, there will be 10 choices. If we were visiting 2 cities, there will be 10 times 9 or 90 different itineraries. Right? So the more cities that we're putting on our itinerary, the more possible paths there are between all the cities. So we'd expect it to grow, and that's what we see here. Right? If we were to allocate these to 4 more slots, we would be effectively multiplying by 4 times 3 times 2 times 1. That would be multiplying by like 24. And that seems about reasonable, right? 24 times 1.5 is about, say, 36 or so. And that's what we had up here. It's 3.6 million. Now, we might even want to go a little bit further than this. And we might say, well, if this kind of a situation comes up often, where I want to allocate n things to, let's say, k, or I always forget which variable uses r. Okay. When I learned it with k, but a lot of places use r as the second variable. So if I want to allocate n distinct items to, say, r slots, where r is less than n, where order matters, and without replacement. So this kind of a scenario, I might actually want to give this a name, this ratio of factorials. I notice that where I pick up the factorial to complete it, well, in this case, this was 10 minus 6 is 4. So I could view this as 10 factorial on the top over, well, 4 factorial is 10 minus 6 factorial. And now instead of having like 10 and 4 explicitly appear in my formula, where 4 doesn't have a direct relationship to the numbers in the original problem, it has like an indirect relationship in that it's the number of left out cities. If I rephrase it as 10 minus 6, I now see that I have a formula that's only using as inputs the 2 numbers from my original problem statement. There were 10 cities to pick from, and there were 6 cities we were going to visit. We call this 10p6. The p stands for permutation. If you think of the word to permute, it means like to kind of rearrange. So when we say like how many permutations are there of something, how many different rearrangements. In other words, if I take the same things and rearrange them, I count that as something different. That's a different permutation. So order matters, because if I permute things, that's a different permutation. Order matters here. So in general, if I have n distinct objects going into R slots without replacement, so when I use up an object, when I allocate a specific object to a specific slot, I can't allocate that object again to future slots. And order matters, meaning that if I took the same allocation to the slots and jumbled it up, that would be a different outcome. In this case, that would be a different itinerary. Then the number of outcomes we say is NPR, or it's n factorial over n minus r factorial. And actually, you might have noticed, including when I went to look up what variable it uses, you might have noticed that NPR is actually in our calculator. If we go to that same math probability menu, we see NPR is number 2 here. Now, if I just go down to NPR, the calculator gets kind of confused. It wants to use like the previous answer. This NPR operator is a binary operator. So the same way if I just typed in plus or something, it would be like, well, what comes first? You know, it wants to see something like 3 plus 5. So if I wanted to use the NPR button, I would type 10, then the NPR button, and then 6. So just like if I wanted to do 10 plus 6, I would do 10 plus symbol 6. If I want to do 10p6, I do 10 NPR symbol 6. So it takes 2 inputs, one in front, one at the end. It looks a little strange when it's like this, but it makes sense if you think about how like a plus or times or minus sign works. This works the same way. So I want to do 10. Then I'll navigate to my math probability menu. Oh, how did that happen? And then I'll go to my NPR option 2 here and hit enter. So I now have 10. That's the number of distinct items I'm picking from. NPR tells me what operation I want to do. I want to do permutations. And then 6, the number of slots that I have. And we see that again is 151, 200. So exactly the same answer. Now, an important note here. I'll even put a little, I would write it in red, but I've already used red. So I'll put a star next to it. An important note. I'll put an exclamation point after it also. 10 factorial, I mean, it's 3 million, but it's not that big of a number where as far as the calculator is concerned. Our calculators can handle up to 10 to the 99th or so, at least on the 83s and 84s. I think even some of the 84s can handle bigger numbers, and some of the more recent calculators can handle bigger numbers. But we're really capped at about 69 factorial. So if we look at 69 factorial, that's about 10 to the 98th. If we try to do 70 factorial, what happens? At least on this calculator, and again, if you have a more recent calculator, it might be able to handle this, but at some point, if we put a big enough number into the factorial, we're going to get an overflow error. In other words, the calculator is telling us the number that you're asking me to output is too big for me to handle. So I don't know how to handle it. So it can do 69 factorial or any smaller factorial, but not 70 or any larger factorial. But what if I want to do like 70p3, right? If I want to do 70p3. On one hand, I could calculate this as 70 factorial over 70 minus 3, 67 factorial. But if I try that, the way my calculator analyzes it, it says, okay, you want a ratio of two things. The numerator and denominator are complicated. I'm going to simplify the numerator first. I'm going to figure out what is 70 factorial. And then, the strategy would be figure out what is 67 factorial and then divide the one by the other. But when it says I'm going to figure out what is 70 factorial, it says, oh, wait, this number is too big. Frowny face, I can't do that. The calculator isn't quite smart enough to look forward and say, oh, wait, like 70 factorial and 67 factorial have a lot of the same factors. This is just going to be 70 times 69 times 68. That's a perfectly manageable number for the calculator to do, right? I mean, 70 times 69 times 68 doesn't have any problem doing that. It's the problem with calculating 70 factorial. If you have to calculate a permutation like this, it's good to use the permutation button. If we go to math, option 2, if we do 70p3, it calculates it just fine. When it's in the permutation kind of function or like operation, it does things a little smarter. My guess is that it basically does things the way that we didn't want to do it. It basically just runs a for loop for, I equals 1 to 3, multiply n by, multiply like n minus I plus 1 or something like that by itself, and does it that way. So the calculator in NPR mode is just going to do this. That's a perfectly reasonable end result, so it can do it just fine. But if you try to type it in manually, like this, the factorials, well, at least one of them in this case, is going to be too big, and it can't compute it, it can't simplify that fraction. Even though, like, we could look at this and say there's going to be a lot of cancellation, everything's going to cancel except these three factors in the numerator. The calculator isn't smart enough, so to speak, to look ahead to that. So if you're doing permutations or combinations, which we'll talk about in a minute, the better option is to use that NPR or NCR function over here instead of like manually doing the ratios of the factorials. So when I'm showing the ratios of the factorials in previous examples, I was mainly showing it just to show you that the two were the same. But the better option is to use the NPR or NCR buttons. That eliminates any chance of overflows. Now, as a side note, of course, we could have a permutation, whatever, 1000 p 300 or something like that. I don't know, that's probably going to be way too big. If we had a permutation where the end result was bigger than what the calculator can handle, well, then our calculator just can't do that problem. That's just too big a problem for this calculator. But there are, I think, one or two problems on the homework where, particularly the birthday problem, as it's called, where if you try to do it in the factorial form like this with ratios of factorials, it's probably going to overflow the calculator, but just make sure that you do it in the permutation mode and you'll be fine. Your calculator should be able to handle it just fine. Okay. So that's our lazy traveling salesman. And there's our permutation rule written out. When we have n distinct items to be allocated to r slots, where r is less than n, where order matters, the number of unique outcomes is NPR equals n factorial over n minus r factorial. Now, one little note, do we really need r strictly less than n? What if r equals n? What if the number of slots equals the number of items to distribute. Well, then we're just back in our factorial rule, right? It would be really nice if for this formula, if I put in R equals N, I got my factorial rule back. What is NPN? That's N factorial over N minus N factorial. Or that's N factorial over 0 factorial, right? If I define 0 factorial to be something like 0, this doesn't make sense. If I define it to be 1, though, like we defined it above, this is just N factorial. We define 0 factorial to be 1. That's exactly what we'd expect. We recover our factorial rule from the permutation rule. The factorial rule is just a special case of the permutation rule. Permutation rule is a generalization of factorial rule, where we have the same setup, n distinct items to be allocated to some slots, where order matters and without replacement. If that number of slots happens to equal the number of items, we get the factorial rule. We get our denominator just ending up as 1 and no explicit denominator in the answer. But if the number of slots turns out to be something different than the number of items, of course, it can't be greater than the number of items. I couldn't fill up the slots then. So if it's less than the number of items, then I get my permutation rule with this, where did I put it? With this explicit denominator here. So we really could even expand the permutation rule if we wanted to, R less than or equal to n slots, and we wouldn't lose anything. We would just get the factorial rule as a special case of the permutation rule. Okay, and then the third option here, the third type of salesman that we're going to look into is the lazy. So lazy in the sense that has a certain number of clients but isn't going to interact with all of them. But now online salesman. So now we're in more the current era. Suppose a salesman is supposed to meet with 10 different clients, but only plans to meet with 6 of them. So that's the lazy part, not meeting with all of them. But these days we're able to meet remotely, right? We can meet like we're doing here. So the order of their meetings doesn't really matter. If I meet with, oh, wrong, was on the wrong window there. If I meet with the client in Pittsburgh, then LA, then Orlando, then Wheeling, then Cleveland, if there are Zoom meetings, if I do that order, or if I meet with the Cleveland first and then LA and then the Orlando and then Wheeling and then Pittsburgh, that's basically no more or less costly for me, right? I don't have to actually travel to these places, so there's not really any efficiency to be gained by ordering them one way versus the other. Here, order doesn't really matter. It doesn't really matter who I meet with at 9 in the morning or noon or 3 p.m. The only difference in any itinerary, so to speak, or agenda for the day is going to be who I meet with. Doesn't really matter the order. Maybe it matters to the person in LA if I tell them I want to meet at 9 a.m. and that's whatever 6 for them. They might not be too happy, but I mean, as far as optimizing anything like travel time or costs or anything like that, the order doesn't matter in this case. But note that I'm still not going to visit. I'm still not going to meet with the same people twice. So we're still doing this without replacement. If I meet with the folks in LA at noon, I'm not going to meet with them again at 3. I'm still doing it without replacement. But in this case, order does not matter because these are online meetings. There's no physical travel or physical distance to worry about. So we can reorder them and it's basically the same agenda, one way versus the other. So what do we have now? We have a bag of 10 cities. I'm just going to call them A through J. I have 10 cities. 10 cities or 10 clients, but I'm meeting with them remotely. And again, I have 6 slots. I have 6 clients I'm going to meet with. I can do something kind of similar to before where I'm going to pick out 6 clients, put them into 6 slots. And then I'm going to put the remaining 4 clients into this other bag at the end here. They're the leftovers. Okay, so I would have maybe 10 choices for the first, 9, 8, 7, 6, 5, and then 4 going over here. So let's take this as a jumping off point. My number of, let's say, agendas, kind of a strange thing to say because agenda is already plural, but agendas, number of agendas is something like this, but this would be if order mattered. If order mattered, this is what my answer would be, right? This is what we just did with the permutations, which would be 10p6 or 10 factorial over 4 factorial. If order mattered, this would be the correct answer. But the thing is that order doesn't matter. But order does not matter. So if I were to write 10p6, or if I were to write 10 factorial over 4 factorial and call that my answer, it would be incorrect. But exactly how would it be incorrect? It would be incorrect by a factor of the number of rearrangements of these. Maybe I shouldn't circle the numbers, but the spaces. Maybe that will make it a little more clear. Right, if I had city B and then city D and then city A and F, J, and H, I don't think I reused any. No. Under the red scenario, the 4 in the second bag, order doesn't matter. They can be jumbled about, no problem. But under the red scenario, these 6 have to be in this order. If I change the order, that's a different outcome. It's a different agenda. But I don't want that to be true. So if I were to impose that order matters, I would have the wrong answer here. I would have the wrong answer in that I've overcounted the number of agendas, because if I say swapped B for D, I want that to be the same agenda, but the red calculation would have counted that as 2 different agendas. So what have I overcounted by? I've overcounted by a factor, by a multiplicative factor, that's as many reorderings of these 6 as there are. That's the number of ways to allocate 6 cities to 6 spaces. I've overcounted by how many ways can I allocate 6 distinct items to 6 slots by 6 factorial. So again, if I were to just take this naively and go through the calculation I did just previously, I would get 10p6, I get 10 factorial over 4 factorial. But that would only be the answer if order mattered. But here I'm saying order doesn't matter. I don't want order to matter. So this red answer would overcount by the number of rearrangements of these 6 cities in these 6 slots. It overcounts by a factor of 6 factorial. So 10 factorial over 4 factorial is 6 factorial times too many. So what do I want my answer to be? I want to divide that by 6 factorial to correct for the fact that the rearrangements of these 6 cities in these 6 slots all represent the same agenda. So this is my number of agendas. And we have a name for this as well. We call this 10C6. So C stands for combinations. And often we would just use the word choose instead of C. So we'd say 10, choose 6, or just 10C6. This also has a notation that looks like this. It looks like a fraction in parentheses with one number divided by another, except that the parentheses have to be there. With fractions, if I had like 10/6, I wouldn't have to write the parentheses all the time. But here, these parentheses have to be there. And note that there is no dividing by line, right? There's not a line like that. It's just a 10 up top and a 6 on the bottom inside of parentheses, no division line. So that's also a way that this is often written. And this is actually a formula that comes up quite often. So things like expanding out polynomials or the Pascal's triangle. So in some of these other algebraic areas, it comes up in areas that you might not quite expect. The binomial theorem, this 10 choose 6 or this n choose r in general, comes up in a lot of different areas. So for this one, again, I could, come over to my calculator and do 10 factorial over parentheses 4 factorial times 6 factorial. That would give me the answer. But here I'm just like the NPR, I'm going to use the NCR operation. So to get the answer, I want to do 10, then I'll do math, over to probability menu, down to NCR, 10 choose, or 10C6. And that gives me actually only 210 agendas. So 210 possibilities for what that day might look like when order does not matter, when it doesn't matter who's first and who's last, because we're just Zoom meeting them. It does, there really aren't geographic constraints or anything like that. So if LA follows Pittsburgh, that's no more costly than, say, Wheeling following Pittsburgh. Okay, so again, the general combination rule, when we have n distinct items to be allocated to r less than n slots, where order does not matter, that's the big difference here, where a different reordering of what we've allocated does not represent a different outcome. The number of unique outcomes is given here. And again, we might want to ask ourselves, what should happen if r equals n in this formula, and what does happen? What should happen if I allocate all of my cities to slots in a given day? Well, there's only one agenda then, right? I have to meet with all 10 of my clients. Doesn't matter what order, they all kind of the same agenda. I'm just meeting with everybody. There should be one agenda. There should be one outcome. What is NCN? It's n factorial over n minus n factorial, just replacing r with n, times n factorial. This makes a 0 factorial, which remember was 1. I have n factorial over n factorial is 1. Exactly as I'd expect, right? So again, why is 0 factorial 1? Well, one way to think of it is there's only one way to allocate 0 things, and that's to not allocate anything. Another way to think of it is it makes these formulas consistent. I could actually let r be less than or equal to n, and that would be fine as well. I could also ask something like, NC0. If I didn't want to meet with any of my 10 clients today, what would that look like? N factorial over n factorial times 0 factorial. That's 1. There's only one way to not meet with any clients today, is just to not meet with any of my clients. There's no second agenda. Any questions on any of this? So this stuff can be a little bit abstract. And as kind of a side note, if you go poking around either in the textbook or online, people like to talk about poker hands and things like that. And they like to talk about things like what's the probability of like, getting a pair on a 5 card poker hand or getting 3 of a kind on a 5 card poker hand. And that's actually more of a difficult problem than it seems like. To get, say, 3 of a kind, to have your hand be 3 of a kind, like you can't get 4 of a kind, right? So if I have 3 3s and then also have another 3 and a 2, well, that's actually a 4 of a kind. Or if I had like 3 3s and then 2 10s, that's actually a full house. So that wouldn't be considered 3 of a kind. I so if you get into these like poker hands and stuff, the the calculations become more challenging because you have to exclude other scenarios. And it becomes more challenging because of the context. You just kind of need to know poker. You need to know that, oh, okay, like if I had 3 of a kind and then another 2 of a kind, that would be something that would be a different kind of poker hand that I wouldn't call 3 of a kind. So you need to know quite a bit more background. So don't, get discouraged in that situation. We're sticking to the more mathy kind of questions in this course. However, if you like poker and if you want to investigate that, um, at this point, you have the background that you could investigate that if you wanted to. If you understand poker and you understand the different hands, it'll make a lot more sense why they're, you know, taking this thing with a whole bunch of combinations in it and then like subtracting off maybe something else. Uh, they might be looking at the 3 of a kinds overall, say minus the 3 of a kinds that are full houses or something like that. Any questions on section 4.4? Okay, then let me stop the recording.